Okay, so I'm going to quickly go through the solutions for this last exam, and if you have any questions, please feel free to ask me, but we got to get going on Chapter 10 right away, so I'm not going to spend time in class going over the solution. Alright, so the first problem was just a warm-up problem, take a derivative, and this is a little more than a warm-up maybe, but just some algebra. So we'll do this one first, sine 2x minus cosine of 3x. I want to find the second derivative of that. So let's take a look. Wait, what is it again? I got it. So sine 2x minus cosine of 3x. So we've got number 1. Sine of 2x minus cosine of 3x. And then I want to find y double prime. So basically sine goes to cosine, cosine goes to negative sine. Each time I do that, the chain rule requires I pull out a 2. So sine to cosine, cosine to negative sine, so that'll become negative 4 sine of 2x. And then for this one, cosine goes to negative sine goes to negative cosine, so it's negative negative, so that becomes a plus. Chain rule again twice. This will become 9 cosine of 3x. The purpose of this one was to kind of get you used to taking derivatives and second derivatives and what you'd use later on for the differential equations. Okay, so the second one, B, is, let's see what that was, 5x minus 7. So we want to decompose 5x minus 7 over x squared minus 3x plus 2. Well, we can see that this is factorable, so it's 5x minus 7 over x minus 1, x minus 2. So I'm going to set this up, and I'm going to say that 5x minus 7 over x minus 1, x minus 2, these are nice easy linear factors down here, so that just becomes a over x minus 1 plus b over x minus 2, okay? And now we want to multiply, the fractions are going to be a hassle, so I multiply through by this whole thing, so that gives me 5x minus 7 equals a times, well, the x minus 1s will cancel, so I'm just left with x minus 2, plus b times the x minus 2s will cancel, so I'm just left with x minus 1. Now I pick convenient values of x. If I say x equals to 2, well, let's do x equal to 1 first, because that gives me my a. So 5 times 1 is 5, minus 7 is negative 2, equals 1 minus 2 is negative 1 times a, plus, well, 1 minus 1 is 0, so that goes away, 0b. So negative a equals negative 2. This gives me a equals 2. And then my other convenient value will be 2, x equals 2, because that will make this go away. So 5 times 2 is 10, minus that's 3, equals 2 minus 2 is 0, plus b. So that's pretty nice. Then I have b equals 3. And so that means this whole thing, when it's done being decomposed, will equal 2 over x minus 1 plus 3 over x minus 2. And I put a box around that final answer, and I didn't do that up here. Okay, so on to number 2, and I think this is the first little bit of calculus we had to do. Let's take a look. We had the integral e to the x cosine of 2x. Okay, so integral of e to the x cosine of 2x dx. And let's see, what did I say? Oh, I told you to use integration by parts. All right. So the game here is to pick something that's easy to differentiate or easy to integrate. These are about equal as far as their integration and differentiation. So I'm just going to pick my u equals e to the x. So then du equals... actually, no, I'm going to go the other way around because it's a little bit easier to differentiate this because of the chain rule. So I'm going to do it just a little bit easier way. I'm going to use cosine of 2x as my u. Cosine of 2x. So that means du equals negative sine of 2x times 2. And then here I'm going to put my dv is going to equal e to the x dx. I probably could have fit that there. And then so v equals just e to the x. Alright, so now I plug this into uv minus the integral of v du. And I've got, well, u times v is e to the x cosine of 2x again. But it's no longer an integral, right? That's just a function. Minus the integral of v du. So it's the integral of v, which is e to the x, du, which is negative sine of 2x times 2. So it's a negative 2. So I'm going to put the plus 2 out here. So it's e to the x sine of 2x dx. Well, I didn't make much progress here because this is not really much better looking than my previous one. But it's kind of the same form, and over here I did the derivative of sine is cosine, but the derivative of cosine is negative sine. So I can get back to cosine if I do integration by parts again. So I'll do the same thing. U equals, this time, the sine of 2x dx, and then so that means du equals the derivative of sine is cosine 2 cosine of 2x dx, and then here I'm going to say that my dv equals e to the x, and then so that means v equals e to the x again. So I'll rewrite this whole thing. This whole integral equals e to the x cosine of 2x plus 2 times this integral, right? And so this will be u times v, so it's e to the x sine of 2x, e to the x sine, so it's uv plus, or minus the integral of v du, minus the integral of v, which is e to the x, du. Put the 2 out here, and so that's e to the x cosine of 2x dx. Alright, well, still, I didn't get much easier, but what I do notice is that it is the same as I originally started with. So I can write here that, I'm running out of room a little bit, that the integral of e to the x cos 2x equals e to the x cos 2x plus 2 e to the x sine of 2x, and then minus 4 e to the x integral e to the x cos 2x dx. Well, here I have e to the x cos 2x, integral of e to the x cos 2x here, so I'm just going to add all these over to the other side. So now I've got 5 times the integral of e to the x cos 2x dx equals e to the x cos 2x plus 2 e to the x sine of 2x. And then I remove that integral to the other side. So if I want to get just this final integral, I divide through by 5. And that's supposed to be a 5, just for the sake of the notes. I'm going to make that a better 5. So this is a 5, right? 1 plus. And so now I can just go through and divide this thing by 5 here, and then divide this sum by 5. And so it's this thing. And then, of course, we have to put plus c. And just for the sake of nice notes, I'm not going to rewrite this. Just cancel those out, put a box around my final answer. Like that. Okay? So there's number 2. Let's take a look at number 3. What was number 3? Number 3, integral from 0 to 5 over root 2. Wow, that's a strange limit of integration. 0 to 5 over root 2. So this is number 3. Integral from 0 to 5 over root 2 of dx. What is going on here? Dx over, and to make sure I get this right, 25 minus x squared. Dx. Okay, now hopefully by now you kind of see, well, I've got this kind of a difference of a a constant and a variable squared under a radical. This is going to be a serious hassle, so we use a trig substitution. Well, let's see, this is something minus variable squared, so I know that sine squared plus cosine squared equals 1, so if I subtract, I say cosine squared equals 1 minus sine squared, and that looks like this, constant minus variable squared. So I'm going to say that x equals, I want it to look like this, 5 sine of theta. What does that mean then? That dx equals 5 cosine of theta, d theta, and most importantly that x theta equals the arc sine of x over 5. Okay, we did one of these in class the other day. So that means that when I replace these limits, when I rewrite my equation in terms of theta, I'm also going to replace my limits. So let's see how that shakes down. So let's do the bulk of it here first. 25 minus x squared is going to be, well, let's put the dx on top, so it'll be 5 cosine of theta. 5 cosine of theta, d theta. Look at what I did up here. I did the exact same thing I did on the exam. What an idiot. Alright, let's put a 1 up there. Erase. I don't know what's up with that. Why did I do that twice? 1 over 25 minus x squared. So I replace that dx with a 5 cosine of theta. This becomes square root of 25 minus the x squared, which is 25 sine squared theta. Well, this becomes, I can factor out the 25, I can factor out the square root of 25, which becomes a 5, so that cancels. And this becomes 1 minus sine squared, which is cosine squared. Alright, so let's, but what about my limits of integration? So my theta here, my upper limit becomes, let's call it theta upper equals the arc sine of root 5 over 2, 1 over root 2 equals root 2 over 2. So where is the sine root 2 over 2? That's at my upper limit is going to be pi by 4. Alright, so this gets a pi by 4 up here. And then where is the sine equal to 0? Well, that's at 0. So that just becomes this thing here. So this will go to 0 to pi by 4 of, let's see, 5 over all this stuff. So, ooh, that's interesting. So this becomes 5 cosine theta d theta over 5 times the square root of 1 minus sine squared is cosine squared. So this cancels out. And the cosine theta over the square root of cosine theta, that cancels out. So I'm really left with just integral from 0 to pi by 4 of d theta, which just equals theta from 0 to pi over 4, and that just equals pi over 4. Okay. So we can leave it in pi over 4. We can leave our integral in terms of theta here because we changed our limits in terms of theta. You can't leave the 0 and the 5 over root 2 here. 4. And what was 4 all about? 4, I think, was an improper integral. Yeah. 1 to infinity of 1 over x dx. Okay, there's a couple ways you could do this. I get, a little bit sloppy, but it really kind of makes more sense, is just to leave my infinity right in here. Well, this equals the integral of 1 over x is just the natural log of x evaluated from 1 to infinity. So that equals the natural log of infinity minus the natural log of 1, which equals infinity minus 0, which equals infinity. So this thing doesn't converge, so this thing diverges. Alternatively, you could rewrite this thing as the limit as b approaches infinity of the natural log of x from 1 to b, blah, 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 and that comes up to the same thing. That still comes out to infinity, which you wind up just sticking your infinity in for b anyway. So these two work out the same. So this thing diverges. Okay. Number 5. And number 5 was dx over root x 1 plus x. I did it again. What's up with this? Huh. I gotta be careful. It says change. Oh, it says find the value to which it converges. All right, so this must converge, and it changes the limits of integration when you make the substitution. So we're supposed to make some sort of substitution, and I should change the limits when I do that. Well, let's see how this shakes out. Integral from, what is it? 0 to infinity of 1 over root x, and then it's 1 plus x, I think. 1 plus x dx. So this one, there's a couple ways you could do this. I'll do it the longer way first, and I'll just show you what you could have skipped. I'm going to say that u equals the square root of x. And so that means that x equals, what does x equal? U squared. So that means dx equals 2u du. Alright, so when I substitute all this stuff back in here, well, if u is the square root of x, the square root of infinity is still infinity, so that doesn't change much. So we go from 0 to infinity still. Now, notice I've changed this. This is now an infinity in terms of u. Doesn't make a difference, but I was careful here. And then this becomes 1 over u times the quantity 1 plus x squared. Ooh, okay. Oh, 1 plus u squared. And that's times du. Now this looks like a potential trig substitution problem. Or I could say that 1 plus something squared, it's like 1 plus tan squared, or 1 plus cotangent squared. I think tan is easier, so I'm going to say that u equals tan theta, and then so du equals derivative of tangent is secant squared theta d theta. And so now my infinity becomes a little interesting, right? So my theta equals the arctangent of u. So where does, if I need to get an infinity up here, if my u is infinity, the arctangent of u, right? Where does the tangent become infinity? Sine over cosine. Well, it's when cosine goes to 0, so that equals pi over 2. All right. So I can rewrite this in terms of theta now. And, oh, d theta, where is my, or du, oh, I got that here. I think everything. So now my, so this is my theta upper. And where is the tangent? I should write that as theta lower. Where is the tangent equal to u? 0? Well, that's at 0. Okay, so that 0 is going to remain as 0. So I can rewrite this thing now in terms of theta. And let's see, the 0 stays as 0. This becomes a pi over 2. And the du is, oh, I missed a 2 here. Dx, oh, yeah, I knew I missed a 2. So this equals 2. Okay, so because dx equals 2u du, so dx has got to be 2u du. All right, I missed that stuff here. Okay, so what happens now is let's see, rewrite this thing is, so this becomes 2, u is tangent of theta, and then du is secant squared theta, d theta, all over u, which is tangent of theta, and then 1 plus u squared, 1 plus tangent squared. Well, 1 plus tangent squared is secant squared. All right. So let's see, this is pretty nice. Tangents cancel, secant squareds cancel, and once again I'm left with a pretty easy integral. This is 0 to pi over 2 of 2 d theta, right, which equals 2 theta evaluated from 0 to pi over 2, and that just equals pi. All right, that's our final answer. Put a box around that. Okay. Now, notice I made some mistakes here, right? I forgot that 2. I caught my mistake. But, you know, I give you credit when you're doing stuff right. You're going in the right direction. It may not work out great. You might get a different answer. But if you're doing a good process and it's easy to follow your work, I want to give you credit for that. All right, number 6. What is this all about? Number 6, y double prime minus 4y prime plus 4 equals 0. Y double prime, I think it's minus 4y prime plus 4 equals 0. Well, I know that my solution will look like y equals something e to the rx. All right, so y prime equals r e to the r. Oops. Make that look more like an exponent. E to the rx, and then y double prime equals r squared e to the rx. So I plug all these in here. So it's r squared e to the rx minus 4r e to the rx plus 4 equals 0. for y, this is supposed to be so plus 4 e to the rx equals 0. I can go through and divide out all my e to the rx's, and so I'm left with my characteristic equation, e r squared minus 4r plus 4 equals 0. All right, this is the gist of it. One little catch, though, that this factors out to be r minus 2, r minus 2. So this is a repeated root. The r equals 2 is a repeated root. So our solution is y1 equals c1 e to the 2x, and my y2 equals c2 x e to the 2x, right? And that's from that table in your book, 17 point whatever. So the key thing is you can't use the same solution twice because they're not linearly independent. We've got to change the solution and add that x there. So our final answer is y equals c1 e to the 2x plus c2 x e to the 2x. Right, and that's it. Last one, we're almost done. Number 7. Number 7 was a bit of a hassle, but doable. So theta dy d theta, I'm going to transcribe this very carefully, theta dy d theta minus 2y equals theta cubed secant theta tangent theta. Now whenever you see a secant theta tangent theta, I'm immediately thinking, oh, okay, that's the integral of, or that's the derivative of secant. The derivative of secant is secant tangent. So I'm thinking this would be, easy to integrate somehow later on, hopefully. Well, I want to make this look the right way, so I'm going to divide through by theta. So, and actually, just to save ink, or to save, electrons, I'm going to just call this y prime and y. So I'm going to divide through by theta, so that means that y prime plus a negative 2 over theta equals, divided by theta here, that'll be a theta squared secant theta tangent theta. Okay, why did I do that? Because I want this function to be kind of staring me in the face here. So I know this multiplication factor I need is going to be v equals e to the integral of negative 2 over theta d theta. So let's look at this integral of negative 2 over theta d theta. I'm going to write that as negative 2 times 1, the integral of 1 over theta d theta. Well, 1 over theta d theta, that's not natural log, so it's negative 2 natural log of theta. But what I need to do is, and this is where your knowledge of natural logs come in, I'm going to put the negative 2 up here. All right, so that becomes natural log of theta to the negative 2, which becomes natural log of 1 over theta squared. And e to the natural log of 1 over theta squared just equals 1 over theta squared. So I'm going to multiply this through by 1 over theta squared, and that becomes 1 over theta squared times y prime plus 1 over theta squared here will be negative 2 over theta cubed, times, this is supposed to be a y here. Let's fix that. So times y equals, and 1 over theta squared, conveniently this cancels out to be the theta squared here and the theta squared down here cancel. So this becomes secant theta tangent theta. Alright, well, this is not obvious, but 1 over theta squared is really, I'm going to write this as theta to the negative 2 y prime plus negative 2 theta to the negative 3 y equals secant theta tangent theta. Right, so this is first times the derivative of the second plus second times the derivative of the first. Our two functions here are 1 over theta squared y prime equals secant theta tangent theta. So I integrate both sides and I get 1 over theta squared y equals the integral of secant tangent is just secant theta. Now I multiply out, y equals theta squared times the secant of theta. Alright, now I'm going to, this is my, oh, and then I forgot, plus c, right? And then when I multiply through this, it's plus c theta squared. And I put a dotted box around this because this is, the hard part. Right, but I'm not quite done yet. I have to apply initial condition. Figure out what c is. My initial condition was, let's see, theta is greater than 0, y of pi over 3 equals 2. So y of pi over 3 equals 2. Okay? So when I plug this in here, I know that y, the 2, has to equal theta squared, which is, well, what a hassle that is, pi over 3 squared, times the secant of pi over 3. The secant of pi over 3 is 1 over the cosine. The cosine of pi over 3 is 1/2, so that's nice. That's just a 2. I'm going to write that out because that might be hard to follow. Times the secant of pi over 3 plus c, some value c, I don't know what that is, times this, which is pi over 3 squared. Well, I can do a little bit of algebra here. 2 equals pi over 3 squared times the secant of pi over 3, which is just 2, plus c times pi over 3 squared. And now I just have to solve for c. So c equals 2 minus 2 times pi over 3 squared, all divided by pi over 3 squared. And I can clean that up a little bit and factor out the 2 here. Is that the right way to do it? Yeah, sure. 2 times 1 minus pi over 3 squared over pi over 3 squared. Well, that's not the cleanest way to do it either. What I should have done is written it this way. Just divide through the pi over 3 squared, so it becomes 2 over pi over 3 squared minus 2. And that's your c. So you plug that into here, and then your final answer is y equals theta squared secant of theta plus 2 over pi over 3 squared minus 2 times theta squared. That is the final answer for that problem, which is the last problem of the exam. So that's it. I hope this helps. You learned a little something. We're moving on to chapter 10. See you soon.